All right, hello everyone. So this is chapter 1, part 2. Today we're going over sections 1.5 through 1.10 in your text. I did want to address a couple things from the last portion of the lecture. So for chemical versus physical changes, I went into Alex and I was looking at some of the problems that they're going to give you. And so I should mention I don't like the way they necessarily introduce physical versus chemical changes because they use, what is that? Is that the text? Okay, let me go back here. They use things that we haven't been introduced to yet, like density is a physical property. The density of water is 1 gram per milliliter. The density of steam is much lower. So the physical properties are essentially just changes in physical state or physical arrangement. The actual molecules, and now these are the molecules. When they show you these little pictures, these are the individual molecules. Here, they're all water, and they're arranged in different physical properties, right? These are water in an ice cube, so it's structured and tightly compact. Uh, Water in liquid form is loose and just kind of moves around wherever. And then water in gas form is expanded. It just bounces off of the wall and will fill any space that you put it in. So a room or the atmosphere, the world, whatever, the gas just keeps bouncing and moving around, spread out from one another. So all of these are physical states of matter, and thus the difference between each one of these or just the physical property of the state of matter or the density, different physical properties. Now, we haven't introduced density yet, so it didn't make sense for me to use that to describe physical properties. The best thing I can say about that, and I've included some videos in your Cougar View, and if you want to go on to YouTube, there's also some great, let me go here. Yeah, I've physical versus chemical changes on YouTube, and then kind of watch a couple of those just to see if anything clicks better than it might have in my lecture. Okay, so a chemical change has to do with changing the actual chemical composition. All right, when we look at this image, if I break down a water into hydrogens and oxygens, that would be a chemical change. The molecule is different than the water originally was, right? I've split up the hydrogen and oxygen, and these are all individual atoms. The red ones are the oxygens, the white ones are the hydrogens. And so we haven't introduced the atom yet, so all of this kind of does a circle, and I have to explain one thing to explain another. So I might play with this in the future and see if I can't get a better um, order to cover these topics so that nothing's confusing. But just know that a physical change, just the molecule stays the same. It's rearranged, it's stacked up, it is spread out, but in the end, the water molecule will still be a water molecule. A chemical change has to do with changing the actual structure of that molecule. So water will no longer be water. It'll be something else, peroxide, hydrogen peroxide or something like that, right? So I've changed the chemical properties of this as well. Chemical properties are like smell, color, uh, but even that necessarily can be a little ambiguous, right? Because I don't know, if it becomes a gas, it loses its color, right? So that can be a little ambiguous, but I hope that you can work your way through that. Email me if you have any problems. That was a tougher section. I think I missed one on uh, the last portion, the last objective that you'll have to do. Just they're a little bit tougher word problems getting toward the end, but remember that molecules, if it's a different type of molecule, it's going to have different physical properties, right? If I have liquid water in this hand, liquid hydrogen peroxide in this hand, they're going to have different densities, which we haven't talked about density yet, but we will today, so that's why I'm bringing it up now. They'll have different masses, right, for the same amount of volume, or different volumes for the same amount of mass. All that has to do with density. So when we get there, I kind of readdress that as well. Anyway, all right, let me go back to, we're starting today at 1.5, significant figures. Also have the PowerPoints pulled up on your Cougar View. So if you want to follow along there, that's fine. I'm going to use the text, I believe, because it has a few more things in there. Okay. So first off, counting numbers. When we count numbers, there are distinctions that need to be made between what kind of numbers we're talking about. All right. So an exact number is when something can be counted fully, exactly. For example, 12 donuts in a dozen, right? A dozen is 12. There's no if, ands, 12.5, whatever. A dozen equals 12. When I count by the dozen, I'm counting whole numbers. Okay, so an exact number is something that is defined, it's definite, and there can be no ambiguity or interpretation to it, right? There's a certain number there, that's the exact number. All right, now an inexact number has to do with other things like weight or length or even time, right? If I say that I am 24 years old, I'm not, but uh, I'm 24 years old. Well, I could be 24 years, 6 months, 3 days, 2 hours, 10 seconds, 25 milliseconds. You see how I can just keep going and make it even more precise, right? Same thing goes with measurements in terms of length, right? If I want to say this fish is 53 centimeters, or I can say it's 53.5 centimeters, or I can say it's uh, 53.50 centimeters. Just depends on what kind of tool I'm using to measure it, right? How accurate is the little tool that I have to measure this number? And that's why we say these are inexact. It's really up to the person taking the measurement, right? How precise that number is, okay? So let's talk about, well, we'll do more stuff with measuring when we get into lab. So for those of you in my lab, um, I'll do a lab introduction and I'll have a ruler and some materials that we're going to measure. So you'll see how the eye of the beholder, like the person taking the measurement, has a large impact on what number you get, right? If I look at something, I may say it's 53.0. If you look at it, you may say it's 53.5, okay? And the most important thing that's not a problem, we all see things differently, right? Some people see it glass half full, some people see it glass half empty. Uh, the important thing is to be consistent, right? If you're like to favor the point 0.5, always favor the point 0.5, right? If you like to favor being right on the number, always favor being right on the number. Just be consistent, and that'll lead to more consistent results. Okay? So, what is a sig fig? A significant figure, and I'll say that a lot, sig figs, just to kind of abbreviate it. Sig figs are all whole numbers, so 1 through 9. Anytime you see that, that's considered a significant figure. All zeros after the decimal. If you see a decimal, then every zero after that is significant. And then all zeros that are in between counting numbers 1 through 9. Okay, so if I have 505, all three figures are significant. Let me pull up my paint and do a couple kind of examples just to show what I mean by that. Alright, so numbers, blah, there. Let me say 260.35. Alright, I'm going to do several problems. 4,000, let's do 4001, and then 6030.0. Actually, this one will be going 6030, and then let's do just in case you see something like this, 05354.000, or let's say 002. Okay, so I'm going to go through here and say how many significant figures are in each. You try to guess before I get there. So all the whole numbers are significant. So that's the 2, the 6, the 3, the 5. All zeros in between whole numbers or counting numbers. So that 0 is also significant. That would be 5. And then we'll put sig figs. Okay. Next up, 4,000. All right. Zeros before the decimal are significant. But if there's not a decimal, then only the whole numbers are significant. So in this number, I only have one significant figure, and it's that 4 there. Okay. Now I did 4001, so I could illustrate. This would have 4 sig figs because that 1 makes the other zeros in the 4001 significant. Let me do another one here, because you'll see this on your Mastering Chemistry or your ALEKS objectives. Okay, so 4,000 with a decimal at the end. Okay, anytime I add that decimal, it makes all of the zeros in front of it and behind it significant. Okay, so 4,000 with a decimal at the end has 4 sig figs. Okay, and now kind of another example. Remember, the decimal makes all the zeros in front of it and behind it significant. So in this one, 6030.0, I have 1, 2, 3, 4, 5 significant figures. Okay, but for 6030, since there's no decimal, that last 0 becomes insignificant, and that will be 3 sig figs. Okay, and then for this one, the 0 in front of 354 is not significant, but the zeros behind the decimal are, so that would be 6. Okay, make sure y'all can still see all that. Yeah, so I just wanted to kind of, it's easier for me just to kind of show you. You get the gist of it. Most of you have dealt with this before. Your Mastering Chemistry or ALEKS objectives will have you add and multiply these. So let's kind of talk about that really quickly. Anytime I am adding numbers together, let me clear all this off. Let me come up here and clear that off. And let's do plus 12.2. Okay. So this is an equation. Let me take that off. Alright. That should be a plus, so I can't really write. So 260 plus, let me see if I can do a little different. Clear that off. Let me see how this will work with my dang 260. Oh, it's so ugly. I can't draw the mouse. Point 32. All right, and then let's say plus. And anytime you're doing addition or subtraction of decimals, you want to make sure that you line up the decimals. Okay, so this is an addition problem. When you are adding or subtracting significant figures, you have to use the number of significant figures, or excuse me, you will always go to the decimal place of the least significant figure. Alright, so in addition and subtraction, that means that whichever one has the least amount of precision. And so when I say precision, precision is how far to the right it goes. Okay, so you want to find the one that stops furthest to the left. In this case, it would be the 12.1. If this was 12.10, they'd stop at the same place. Alright, if this was 12.100, that makes this one the end. Okay, so just wherever the least precise decimal is, or digit, that's where you have to stop after you do your addition and subtraction. So for this one, I have to stop in the tenths place, right? So just remember the names of these different place values, right? This is the single, the 10, the hundreds. Going the other side of the decimal, it's the tenth, the hundredth, and the thousandth. Okay? Let me take all of those off. All right. So for this one, I have to stop at the tenth place. So my final answer will be to the tenth value. All right. So the final answer would be 272.4. 272.4. Okay. And I stop here because that's where this one stopped. If there was another one up here that just say was 11 and had no decimal, I would have to stop there at the tens place. Okay. So let me clear this off. How do I do that easily? No, don't do that. Let's just do a new one. Don't save. Okay. For multiplication of significant figures, sorry about that, got hung up a little bit. I keep shaking my desk. I know that can't look good. 43.4 times, let's say 2. Okay, so this is multiplication. So for multiplication, I have to use the same number of significant digits that I have in the least, whichever one has the least number of significant digits, that's how many I'm allowed to use for the answer. So 43.4 has 3 sig figs, right? Oh, that was hard to write. 2 has 1 sig fig, so my answer can only have 1 sig fig, okay, because the 2 is the least amount of significant figures. 2 times 43.4 would be 86.8, but since I can only have 1 significant figure, I'm going to round that up to 90. Okay, so that division is the same thing. Let's do one more example. File, new, don't save. Make sure y'all can still see me. Let's do 302 times 23.6. 23.65. Now for multiplication, it doesn't matter if I line them up, okay? So I'm going to go onto my calculator and type this in. 302 times 23.65. My answer is 7142.3. Okay, so now I go back and count the sig figs in each of the numbers that I used in my problem. 4 for this one. So whichever one's the least, that's how many I have to use. So 3 sig figs, I can only use 3 sig figs here. The answer will be 7,140. Oh, I hate how ugly that is. But I hope everybody kind of gets the gist of what I'm trying to do here. Alright, so you'll have a few problems like that, adding, multiplying significant figures, and so their program's going to require you to have the correct number of significant figures. Alright, so let me go back to the text. And then you have all these rules here, so you can go through and kind of do that. I just wanted to do some examples. You got some self-tests, some practice, stuff like that. Always a good idea. And so basically, yeah, this is pretty much what I just went through. Okay, and they'll throw you a couple little curveballs, like they may have you add something and then divide it, or do an average where you have to add 3 decimal numbers with decimals, right? Then you have to divide by 3. So do you use the plus addition rules or do you use the division multiplication rules? Um, I'll let you kind of determine how that all works out. But typically, for like an average, you would use the plus and minus multiplication rules. And it'll kind of go through there and it'll tell you when you mess up. Email me if you have any other problems. Alright, so next up is scientific notation. Alright, so scientific notation is just a way that we can write numbers that are either really big or really small, but we can write them in a way that is easier to read, okay, and easier to deal with. If I have to write, 2 million 100 times in a paper, that can really take up a lot of space. So we use these scientific notations, and we need to be able to use them to multiply, add, subtract, whatever as well. Okay, so being able to work with scientific notation is very important. All right, so let me use, which one am I going to use here? Let's go back to the PowerPoints just to see what they have for this section. Okay, so this is good. The coefficient is the number that is in front, and then the exponent is how the power that 10 is raised to. Okay. So a lot of time it's just moving the decimal. Let me pull back up my paint and kind of show y'all this. New show, yes. Paint, transition. Alright, so say we have let's do 2 again, 2,576,000. Okay, and I want to write this in scientific notation. The first thing I do is take the first whole number and we're making that the coefficient. Okay, so 2.576 times 10. Now I have to figure out what power that it's raised to. Okay, so my 2 is in the single digits place right here, right? So let's imagine it's there, and I'm going to move the decimal all the way back till I get to there. Or I'm going to move the 2 all the way back till I get to here, to the right, right? 1, 2, 3, 4, 5, 6. Okay? So that would be 10 to the power 6. So that's all you're doing. You're moving it to where it should be in the coefficient, right? This single digit places. Let's do another one, and I'm going to go the opposite way. Don't save. Okay, so now let's have 0.0000373. Okay, so now I want to write this as scientific notation. Remember, start with the first whole number. That's your coefficient, 3.73. Actually, let me take away that little circle there. I don't like it. Now, 3.73. I'll do times 10. And same thing, except for this time it's going to be a negative exponent, right? So counting until I get to this single digit place here. Didn't mean to put that. All right. So 1, 2, 3, 4, 5. It's 3.73 times 10 to the negative 5. All right. So that's how you write it. Now let's do some math with it. All right. So let's say I have, let me do a new page. 3.73 times, oh, it's getting uglier, 10 to the negative 5. And I want to multiply it times, let's say the first number we have, which is like 2.35 times 10 to the 6th. Okay? So exponents are actually pretty easy to add, to multiply and divide, because you just subtract or add the exponents, right? So this is a multiplication problem here. I'll do it both ways though. So 3.73 times 2.35, do that first on its own. 0.35 times 3.73, 8.765. So I'll write it all there, but I have to use the same number of significant figures, 3 in this one, 3 in this one. So that means I can only have 3 in my answer. So 7, 7. Alright, now for this, I just do plus 6 minus 5. That'd be times 10 to the 1. Alright, 10 to the 1 is just 10. So my answer, final answer, could either be this, 8.77 times 10 to the 1, or I would also accept 87.7. Okay? So, yeah, just every now and then, you might get confused about whether or not you added or subtracted. Say these were both negative. Remember, if I take a negative from a negative, I end up adding. Okay? So, you have to be careful about little things like that. But just go through and get you some practice in. It's really not that bad. And you'll start to see the patterns and how to figure these things out easily. I think by the end of the Alex objectives, I was doing a lot of these in my head because they're actually not that bad. It'd be like 2 times 3, and then you'd have the exponents. I know 6, and then I'd just add or subtract the exponents, and you can kind of get through this fairly quickly. Also get some work on your calculators. Let me switch y'all back to this. Also get some more work in on your calculators. Typing in scientific notation on your calculator, being able to use it, include the brackets and stuff like that. I'll do, when we get ready to do review, or when I get my whiteboard up, maybe even I'll start doing review problems for the midterm, and we'll kind of work through some more of those then. Okay, but send me emails about problems that you're having with certain practice or whatever you're working on. Screenshot it, email it to me, and I can kind of point you in the right direction and show you where you're messing up. So this is basically everything that we've just done, and most everybody should have done or dealt with significant figures in the past and kind of know how to move that decimal around the way you need to. Alright, so now we have conversion factors. Now I've included some good videos on Cougar View about conversion factors. So with me not having my paint program, hold on just a second, or with me not having my iPad, excuse me, it makes it difficult for me to write out all these conversion factors. So a conversion factor is just a way to set up a problem where you multiply to cancel. Okay, so let me pull up this paint and let me kind of show you what I'm talking about. So let's say they do kilograms and pounds or something like that. Let's do minutes and seconds and hours, because that's something everybody's already familiar with, and you do the conversion in your head all the time. So now I'm going to show you what it looks like to do it on paper. Let's say I have it's been 4.6 hours in a car, and I want to find out how many seconds that is. What I can do is set up these things called conversion factors, and that'll help me keep my units straight as I transition from hours to minutes to seconds. Okay, so let's redo the problem. I've spent 4.6 hours in a car, and I want to know how many seconds that's been. Okay, so typically you would just do it in your head. You'd say 4.6 hours, 60 minutes in an hour, 60 seconds in a minute, so times 60 times 60, there you go. So on a conversion factor, you actually include the units so that they cancel out. I'm going to multiply 4.6 hours times the equality for the hour, 1 hour, which is 60 minutes. Okay, we call that an equality, right? 60 minutes is equal to an hour. All right, but now since I have an hour up top and an hour on bottom, those cancel out. Okay, and now I'm just left with minutes. So this would be 4.6 times 60. equals 276 minutes. And you see how I have the minutes left here up top. So, oh my goodness, I can't write. That would be the first equality. Now, in some of these, you'll have two steps, and so you just carry it on down. Let's see, what would we say? 276 minutes. And I always like to put my first value over 1, because anything over 1 is still itself, right? So this is still 276 minutes. I just like to put it over 1 so I can see the cancellations, right? So now I want to cancel out minutes, so I'll put it on the bottom. And then it's 1 minute, but I'm trying to find seconds, so 60 seconds, right? Now the minutes cancel out. 276 times 60 equals 16,560. I'm going to write it in scientific notation because we just learned that. 656 times, oh, so hard to write with a mouse. 1, 2, 3, 4. Okay, or 16,560. All right, and technically I could only have two significant figures there because I started with 2, so it'd be 1.7 times 10 to the 4 seconds. Seconds was my unit that was left over after minutes canceled out. Okay, so that is conversion factor, and you can use this to do all different sorts of things. You can use it to go back and forth between millimeter and meter, or kilogram and gram. You can use it to go from different units, different things like pounds to grams, or hours to seconds. The conversion factors should be very useful for you for all different types of math problems, even in general everyday life. You can sit here and figure out, like I said, how many seconds, how many minutes we got left, whatever. We do this on a daily basis. We just get so used to doing it that we don't actually see what it is that we're doing, but these are those conversions. All right, so let me clear that off. Go back to and so they're doing kilogram to pound here, which is 2.2 pounds per kilogram. And it's also a good note, you can flip it both ways, right? Whether or not I put 1 hour over 60 minutes or 60 minutes over 1 hour, that just depends on which one I'm trying to cancel out. Okay, so when you go through and multiply, and pull back up Paint, for example, if let's say we're doing meters and millimeters. So 1 meter is 1,000 millimeters, right? But I accidentally leave my value on the wrong side. Say we're 2.76 meters up top over 1. Make sure you can see that little dot. 2.76 meters. If both of these units are up top, then my answer is actually going to look like this, because you have to carry those units over, right? Over millimeter. So just by writing it upside down, I failed to cancel it out. The way I should have wrote it was 1 over 2.76. It's a terrible eraser. 1 over 2.76 meters. Right now my meters can cancel, and I have millimeters on the bottom if that's what I wanted. Okay, so just make sure that you have the conversion factor oriented the right way. Oh, I didn't show that to y'all. Sorry about that. One more time. So if I have 2.76 meters, over 1, but I do my conversion factor wrong on the next step, and I put 1 meter over 1,000 millimeters instead of having it the opposite way where the meters would cancel. My unit, because I have to carry both of these across, would be meters squared over millimeter. Okay, so that's all I was saying with that, is make sure that you have this conversion flipped where it cancels units out and doesn't stack them up. Okay, sorry I lost y'all for just a second there, but I'm back. And this just does several examples of that. As I said, you can go from milligrams to grams. You can use conversion factors to do all different types of problems. And your Alex program will ask you several different ways to do these problems. It'll ask you the answer for some. Sometimes it'll just ask you for the conversion. Now, conversion for temperature is a little different. It's easy for Celsius to Kelvin because it's just plus or minus 273. But for Celsius to Fahrenheit, you're going to want to get some practice in. In one, you have to subtract from Fahrenheit, you have to subtract 32, then divide by 1.8. For Celsius, you multiply by 1.8 first, then add 32. So you have to make sure you keep your order correct. If you do the order wrong, you will get the wrong answer. Okay, so this kind of goes back to order of operations. Uh, Imagine that this Fahrenheit minus 32 is in a bracket. You have to do that first, then divide. If I was going to do it individually, I'd do Fahrenheit divided by 1.8, then 32 divided by 1.8. So that goes back to order of operations. I hope everybody's familiar with that. All right, you have to do the Celsius to Fahrenheit or Fahrenheit to Celsius in a certain order. I've included a video on Cougar View for this as well. Best thing is just to get a couple practices in and you'll have it figured out. Most of the times people just type it in on the computer anyway, but you're not going to be able to do that on a test probably, so I'd go ahead and get some practice in and have an example of it. Okay, so these just show the different scales, just so we're clear. The boiling point of water, Celsius, is set up for the freezing and melting points or boiling point of water. Water freezes at 0 degrees Celsius. It boils at 100 degrees Celsius, and that's where the scale came from. We created it based on water, and so it changes like that. Kelvin is for absolute zero. So absolute zero is negative 273 degrees Celsius. Essentially, that's just what you add to Celsius to get your Kelvin temperature. Okay, whatever your Celsius temp is, add 273. That's your Kelvin temp. I think it's actually 273.15 if you want to be absolutely perfect. All right. And then Fahrenheit we don't use as much in the scientific community because it's kind of like the English versus metric system. The whole rest of the world uses Celsius and Kelvin, so pretty much for all scientific matters, we will use Celsius and Kelvin, but it obviously is important to be able to go back and forth, to be able to convert between the two, because everything that you've heard in your whole life has probably been mostly Fahrenheit. So being able to convert to Celsius will kind of give you an idea of where that is in temperature range, right? Like if I say it's 32 degrees outside, we automatically think Fahrenheit, oh, that's cold. But actually, if it's in Celsius, that's just a normal day, right? So anyway, now last but not least is density. Uh, Density is a measure of the mass per volume. So remember, mass is like the weight of something. The volume is how much space it takes up. Now, we needed a way to express the weight per volume, right? Mass per volume. Anytime I say per, you should think about kind of like a denominator, right? Mass per volume, or let me go back to this. We said minutes per hour, right? Let me clear that off. So there are 60 minutes per 1 hour. So I like to think of per every time I see that little uh, denominator, the division symbol, right? Another example is what we're talking about here, density. So water has a density of 1.0 grams per milliliter. What does that mean? That means if I have 1 milliliter of water, right? 1 milliliter of water will weigh exactly 1 gram. All right. So that's what density is telling you. It's telling you how much weight per milliliter, or how much weight per any volume of any unit of volume, really, and any unit of mass. So I can say kilograms per liter, for example. I can say grams per milliliter. I can say grams per cubic centimeter, because remember we said that a cubic centimeter is the same as a milliliter. Okay, so you'll see density written in probably most always in grams per milliliter, um, but you could see it in other various forms as well. Okay, so I've also included I included videos for density on your uh, Cougar View, but just to kind of show you what they're talking about there, it's a thing called the density triangle. So when you're going to solve for density, I want you to use this thing called the density triangle. New, don't save, and it looks like this. So here's my triangle. Oh, it's so ugly. I could have put a shape in there that time. Um, and I'm going to make a dividing line right here. And I'm going to put another one here. Okay? So this is the DMV. Ought to be easy enough to remember. Everybody's familiar with the DMV. Probably mostly hate it, but this might give you a new light. I like the density triangle. It is a uh, easy method to keep straight when you're going through and doing these calculations. Okay, so the M stands for mass, right? V stands for volume, and we said that density is the mass per volume, and D stands for density. Okay, so the way this works is whenever you're trying to solve for any of these three things, right, density, mass, volume, and you have two of them, okay, so say they give me the density, they give me the mass, I'm trying to solve for the volume. They give me the mass, they give me the volume, I'm trying to solve for the density. I can use this density triangle to help solve it, okay? So, first off, before I do any problems, I want to get back to density and just kind of make sure that we're thinking about it the right way. So, a question, there was like an old trick question that a lot of people ask, and I think it kind of illustrates density very well. So, what weighs more, a ton of bricks or a ton of feathers, right? So, people that have heard this before, they'll say, well, a ton is the same weight as a ton, so the bricks and the feathers weigh the same. But what the question's really playing on is your idea of the density of those objects, right? A ton of bricks might just be like, 100 bricks over here in a pile. A ton of feathers might take a whole stadium full of feathers to make a ton of feathers, right? Because a ton is the mass, right? When I'm looking at my density triangle, the ton is the mass up here at top. What the question really gets you thinking about is the density of these objects. A feather is so much less dense than a brick, right? That it's hard for us to think about the difference that would be in volume to make the same mass. I would have to have, like I said, a stadium full of feathers to make the same mass as 50 or 100 bricks. Okay? So that's kind of the way that I think about density. It's not mass, it's not space, it's mass per space. Okay? So just and a couple other little tidbits about density. Things with less density float higher. So gas has less density than water. So gas always stays above the water. Oil has less density than water, so that's why oil always floats on top. If you have an object that is more dense, like a piece of metal or something, it will sink in water because its density is higher. All right, so that is the relative scale of density, right? Density of water is 1 gram per milliliter. If I have something that's 0.77, it'll float. If I have something that's 1.2, it'll sink. Okay, so this is all kind of a scaling effect or whatever. And the density is just how much mass in a certain amount of volume that uh, compound or chemical or whatever it is that we're talking about is that much mass per milliliter. Okay. All right. So get some work in with the density. Oh wait, I haven't really even talked about it. Let me mention the density triangle. So the master in chemistry or one of your problems, they might give you a density or they might give you a mass and a volume, and you have to find the density. If they give you a mass and a volume, that's easy enough. So whatever they give you, you fill into your triangle here and cover up the one that you're trying to solve for. So say they give me a mass and a volume, I'll cover up density and I'll do mass divided by volume. That'll give me the density. Make sure you put your units in though at the end. Grams per, grams over, milliliter. Okay, you have to leave this little dividing line in there. All right, back it up a little bit. Say they give me the density and the mass. Okay, so I would cover up volume because that's what I'm trying to solve for. Mass divided by density gives me volume. Okay, and that would be the volume in liters probably, or milliliters, whichever the density is expressed in, grams per milliliter might be. That's what you would express your volume as. And vice versa, you would express mass in grams if your density was given in grams per milliliter. Now the last one, say they want me to solve for mass, and they give me the density and the volume. You multiply density times volume on the bottom here. Okay, and that'll give you the mass in grams or kilograms, whatever unit the density uses. Okay, yeah, so get some practice in with the density stuff. Make sure that I've covered everything. Oh, specific gravity, that is just the density relative to water. Remember we said that the density of water is 1 gram per milliliter, 1.0 grams per milliliter. So whatever the density of that substance is divided by 1 is the specific gravity. So that is also the specific gravity. Okay? So it's just a way to compare it to the density of water. If it was like 0.77, then we know that it'll float. Anything higher than 1 would sink. The interesting thing about specific gravity is there are no units for that because the grams per milliliter cancels out with grams per milliliter. Okay? I don't even know if, I don't think they ask any questions about specific gravity. I don't think I will either, but it is good to kind of just heads up. That's what a lot of people will use to kind of determine whether or not something is buoyant in water, right? If it has below 1 specific gravity, it will float. If it has above 1, it will sink. Okay? So, yeah, do some of the example problems. Go ahead and I guess you don't have part 1 of chapter 1 is not due till this Sunday, and so you'll have a lot of time to work on this, get some practice in. Let me know if you get hung up on anything. I'll be around. But yeah, that is it for today. I will see y'all tomorrow and for my lab students. All right, bye.